Okay, so is this light level okay? Are you able to see your stuff? So last time we ended the discussion, but the announcement. So there were some PEXs that were due 2 days ago on the 20th. Well, I haven't graded your, let me back up just a little bit. So today's the 22nd. To be clear, the way the PEX grading goes, my intention for it, is that there's a closed loop of actions. Is that you make some changes, so student posts things to GitHub. I get notified. So I'm the instructor. I make some comments. So the way your PEXs are graded is that there's a silicon component, the part that I metaphorically refer to it as the silicon component. That's the thing that you can run at the MATLAB console. That's the thing when you type test, okay, in each directory. There's other bits where I actually am looking at all the things that you've written, and I check it for correctness and things like that. Metaphorically, I refer to that as the carbon part of your grade. Sort of as a joke, right? Because there's two computers that are grading your PEX assignments. The Silicon one, that is to say my desktop computer, and the Carbon one, which is to say me, right? So I make these, I calculate these things. So the Carbon computer is the meat computer. So the instructor. I do these things, and depending on whether or not you pass all of these things, I give feedback to you on GitHub, and it comes back to you. So the purpose of this is so that it's a closed cycle. You make changes, I make my comments. You make changes, I make my comments. It just goes back and forth until you get 100%. That's the point. Furthermore, there's a little cycle that actually is inside of this one, inside the student one, and that is that you make edits to your .m files, and then you run the test, which is the same test that I'm running. And you keep making these changes until that's right. Then you submit to GitHub. And then I run the same thing and run the Carbon part of the grading and then get it back to you. So the purpose of this is that this is the way software writing programs actually works, is you make little changes and then you test it for correctness and then keep making modifications until it's right. Okay, so that being said, I was sick last week, bad. So the instructor, me, was sick. As a result, the Carbon computer, the meat computer, was out of commission. So I haven't had time to do my part of the contract, right? So I've got to give you feedback. So that that was sad, but I feel better now, so that's great. as a result, the PEXs that were due, so PEXs which were due on Tuesday, which was the 20th, are now due 1 week from that day. Which is the 27th. Also, we haven't posted any homeworks corresponding to last week's lecture for two reasons, actually. One reason because I was just sick as a dog, and the other reason is that on reflection, trying to get writing those exercises, we don't really know enough MATLAB to ask the questions that I want to ask. So we're going to hold that off for a little bit, and then we'll circle back around to last week's lecture, and then have some programming assignments at that time. So we need to learn a few more things before we can have a nice discussion about the algebra of intervals with MATLAB. Okay, so last time we ended talking about Euclidean division. So let's rewrite that and then start going over that. So let A be a natural, and anytime you're talking about naturals in a math class, what do you need to verify? Yeah, you need to verify whether or not whoever's talking about construes 0 to be a natural or not. And in our class, 0 is natural. So let A be natural, and that means that it's conceivable that A is 0. Let B be in this set. So what's the meaning of that set? The positive naturals. Is that in focus? Is that any better? Yeah. Can you see it? Okay. Let A be natural, let B be a positive natural. Then there exists, so that's the meaning of that symbol. And then what does it mean when you write this? That's a good guess. But that's not quite right. So, and it's not exists factorial either, and it's also not exists. Not that one either, right? When you write exists and then exclamation point, this means unique. So there exists unique Q in the naturals, R in the naturals. Well, I guess I could have written Q and R, but oh well. Q and R in the naturals such that A is equal to B multiplied by Q plus the remainder plus R. And the restriction is that 0 is less or equal to R is less than what? B. It's going to be less than B. Okay. So this is called a Euclidean division. Euclidean division. And the individual items each have a name. So A is B multiplied by Q plus R. So I'm writing it a little bit expanded so that I can make the names clear. So A is called the dividend. That's the thing that's being divided. B is called the divisor. That's the size of groups that you're dividing the dividend into. Q is called the quotient. Has an E in it, quotient. And R is called the remainder. Okay. So let's have an example of this, of doing this. Divide, divide 23 by 4, and by divide I mean Euclidean divide. So Euclidean divide 23 by 4. That means that I want you to compute the quotient and the remainder, and I want you to write an equation that says that involves 23, 4, and the quotient and the remainder that you calculate. Okay, so in the end the question is something like this. If there were 23 M&Ms and you were said, okay, break these 23 M&Ms into groups of size 4. How many groups of size 4 could you make? You can make 5 groups. And after you've made these 5 groups, how many would be left over? 3, right? So in grade school, the process usually is written something like this. 4 is outside the house, and 23 is inside the house. And then you take the leftmost digit and you ask, well, how many times does 4 go into 2? 0 times, right? Then you say, okay, well, I'll take another digit. How many times does 4 go into 23? 5 times. And then what do you do with the 5? 5 comes down, multiplies by 4. You write 20 right here, because that's 5 times 4. Then you subtract, and then you have a 3. And then you ask, well, how many times does, well, in the first place, do you observe that what's right here, what we just wrote right here, you can't take another 4 from it. There's not enough to take. If we had mistakenly wrote a 4 there, in that position, then it would have been 4 times 4, and this would have been a 16, right? And then this would be a 7, and you would detect the error right there because 7's no good. Why would 7 be no good in that position? Right, it's more than 4. You could have taken another 4. Okay, so as a result, what is the quotient? 5. What is the remainder? 3. And the equation that relates all of these is what? (23) is what? Very good. Don't you have fond memories from doing this in Miss Harris's class in 3rd grade? Or whatever. Any question about this? Okay. So now what we're going to do is we're going to see how can we define a function that will do this work for us. So let's think about it for a minute. So remark. For the purposes of today, we'll I guess probably a good name for the function would be e. Okay, so e. So we'll define the Euclidean division function. Euclidean division. Okay, so we're going to call it E. But my question is, what's the signature of the Euclidean division function? So, right, there's two inputs. The dividend and what? The divisor. The dividend can be any natural. But what about the divisor? Has to be a positive natural. For the same thing that you've been drilled on all life, in all of your life, that is, it is undefined to divide by 0, right? So there's a natural cross positive naturals input, and what kind of output is there? Natural cross natural, right? Now wait a second, why are there two outputs? The quotient and the remainder, right? So that is to say, to help us understand what was written on the previous page, this one is, we were writing as A, the dividend, B is the divisor, this one will be the quotient, and this one the remainder. Okay, so any question about the signature? Okay, so let's think about this for a moment. We'll define the Euclidean division function with that signature as follows. The Euclidean division of A divided by B is, well, we're going to need cases. Let's think about it. Let's think about a simple case. Or actually, this case is, sometimes students find it a little bit disturbing. Okay, so what is the quotient and the remainder when 23 is divided by 4? This one's easy. 5 and 3, right? What about when 10 is divided by 4? 2 and 2, right? What about when 5 is divided? Oh, no, let's do 6 divided by 4. 1 and 2, right? So now here's the thing. It's obvious, but it's a little bit disturbing until you understand how it works. What is the quotient and remainder when 3 is divided by 4? When 3 is divided by 4. So if I gave you 3 M&Ms and put them right there in front of you on the desk, visualize in your mind's eye the 3 M&Ms, and that's all that's there. How many groups of size 4 could you make? 0. Right? And then after you're done making 0 groups, how many would be left over? 3. So what's the quotient and remainder when 3 is divided by 4? 0 and 3. Okay, so this case, the case when it's not possible to make any more groups, this is the base case. Okay, so how do you detect that you're in the base case? That is to say, the case where it's not necessary to do any more work. When A is less than B. That is to say, when you look down at the M&Ms on the desk and say, there's not enough for me to make a group anymore. There's not enough left anymore. So the base case, the guard to get into the base case is that A is less than B. That is to say, you're not able to make any more groups. Okay. Fine. Pardon me. So in such a case, what's the answer? Right. Q and R, the output, is 0 and how much? Now what does B represent? B is the group size, right? B is the size of the group that you're making. So if you have less than, if you have A M&Ms and A is less than the group size, then what's the remainder? A. All right. Good. So the base case is handled. Well, there's only one other case. That is to say that it is in fact possible to make a group. So that'll be otherwise. Otherwise, and that is to say, at least one more group can be made. And somehow, we're going to have to recurse. We're going to have to recurse. So now, we're going to write something in here, the actual definition, but I want to kind of give you an idea of how we might do it. So let's consider specifically that we wanted to do the grade school problem where there's 23 M&Ms, groups of size 4, and that we're trying to, have a lesson with 9-year-olds, and they're all amped up because they know M&Ms are involved and at stake, So we want to get them all engaged in the activity. So I'm going to construe the answer to this as a group activity among a sequence of 9-year-olds. Okay. So suppose that we've got our 9-year-olds all lined up. They're all, in a straight line. And, well, we give a pile of 23 M&Ms to the first 9-year-old, and we say, okay, we want you to make groups of size 4. And the 9-year-old inspects the current situation and looks at the 23 M&Ms and asks, is it possible for me to make a group? And so what's the answer to that question? The answer is yes. So what that 9-year-old does is they take a group, one group. You can think of it like there's a bucket of M&Ms. They take out 4 M&Ms, right? And they hand the bucket of M&Ms to the next 9-year-old. But how many? What am I trying to say? 18, right? No, 19. There's 19 M&Ms left. So they hand it to the next one. They say, all right, this is what you need to do. There's a bunch of M&Ms in that bucket, and we've been told to make groups of size 4. And so that 9-year-old looks at the bucket and says, can I make a group? And what's the answer to that question? Yes. The answer is yes. So what does that 9-year-old do? They take their 4, right? And now they have those in their hand, and then they pass the bucket to the next 9-year-old, right? And all of them are just patiently waiting, right? Scientists watching the M&Ms. Okay, so now there's 15 M&Ms in the bucket. There's 15 M&Ms in the bucket, and that 9-year-old says to the next one, we need to make groups of size 4. So the 9-year-old looks and says, can I make a group? The answer is yes. So now it goes all the way down to the end. So I'll skip the discussion for a moment and make it to the end. So then there's 11. Whoops, A is 11. Oof. b is still 4. Then a is 7, that's what comes next, and b is 4. And then a is 3, and b is 4. So now I claim that this is the end. Why is that the end? Right. So this 9-year-old has a look at the bucket. Just been handed the bucket of M&Ms and given the instruction, I need you to make groups of size 4. And looks at the bucket and says, is it possible for me to make a group? And the answer is no. It's not possible for me to make a group. So this 9-year-old is the first one that's able to make any conclusions whatsoever. Okay? This 9-year-old is able to make a conclusion concerning the bucket they were given of the quotient and remainder. What is this one able to conclude? And the quotient. Their quotient, right? What is this 9-year-old's quotient and remainder? 0 and 3. So now they determine that the quotient is 0 and the remainder is 3. And so now the 9-year-old that was in the rightmost position now turns to the one that handed him the bucket and said, I have determined that the quotient is 0 and the remainder is 3. But this 9-year-old, if you like, knows that, well, that's not exactly right, actually, because I remember that before I handed you the bucket, what did I do before I handed you the bucket? I took 4 out. So in fact, there's got to be one more. The quotient has to be 1 bigger than whatever I was just told, right? So this one says that the quotient is 0. As a result, what is this one's quotient? 1. So this one says, my quotient is actually got to be 1. What is this one's remainder? It's still 3, right? That actually is correct. And then this one communicates to the next one. So quotient, remainder. So this one reports to the next one and says, I have determined that the quotient is 1 and the remainder is 3. But then this one remembers, well, that's not exactly right, because I remember that before I gave that one the bucket, what did I do? I took a group. So this one says that the quotient is 1, but actually the quotient should be what? 2. What about the remainder? It's still 3. Okay, so I think you see the pattern now. Now I'm going to just fill it to the end. So this one knows that the quotient is 3 and the remainder is 3. This one knows that the quotient is 4 and the remainder is 3. This one knows that the quotient is 5 and the remainder is 3. And then this one, I guess I got to write the arrows here, right? So it'll look nice. Then the leftmost student reports to the teacher and says, the quotient is 5 and the remainder is 3. And the teacher says, y'all got it right. So now you get to eat the M&Ms. And Timmy, you get 3 because I told you to hurry up and you were last in line. So that's the natural consequence of being a slowpoke. Okay. Any question about this? How it works? So what I want you to see, is that in this sequence of events, when is the correct remainder determined? That's the base case, but what I mean is, like, where in this drawing that I just made, where is the correct remainder determined? Right there, right? So the rightmost student, that's the one that has established the remainder, the correct remainder for the rest of time. Okay? No one knew the remainder. The remainder was completely unknown until that position. So this is the position when the remainder becomes known. It wasn't known before that position. And then notice that as the process is moving to the left, when is the quotient known? On the last step, right? Quotient. No. Okay. Now, what I want you to see before we write the answer right here, because remember, we still haven't written the answer right here. The way this works is there's kind of two cases. One of the cases is sort of like you look in the bucket and there's not enough M&Ms to make a group, and you say, oh well, this problem is now small enough that I could answer it right here. Like right here. There's not enough. There's 3 M&Ms, the group size is 4. There's not enough for me to make the problem size is small enough for me to answer it right now. But for this one, okay, when there were 23 M&Ms in the bucket, right, the 9-year-old just looks at that and says, wow, I can't even imagine how many, what the quotient and remainder should be. So what I'm going to do is I'm just going to make the problem a little smaller and then delegate and say, hey, you over there, you do it. Right? You solve this problem. And then all the 9-year-olds, right, they're all, maybe this is management school or something, right? And they just delegate, right? Everyone just takes their handful and then delegate all the way down the line. So what we need to do here is we need to make a recursive call. So I'll make the recursive call and say that Q0, say, Q0 and R is equal to the recursive call. So what are we going to recurse? So this is metaphorically, right, in the metaphor, this is handing the bucket to the next 9-year-old. So we have to recurse. So it'd be what? Uh-huh. A minus B, right? Why A minus B? What is A minus B in the metaphor? Yeah, it's taking the M&Ms. Like, okay, I took mine, and now it's your turn. So what is the group size they're supposed to make? B, right? Everybody's supposed to make groups of size B. So Q0, that's what the 9-year-old on the right thinks the quotient is. They think it's Q0. But they're not right. Why are they not correct? Well, because before you asked them, before you delegated to them, what did you do? You took out a group. So what's the real quotient? One more, right? So the answer is Q0. Well, I'll write it like this. QR is equal to 1 more than Q0 and R. Interesting. Any question about this?
Where are we defining R?
Right here.
Oh, okay.
Which is to say, I mean, look at the picture. Where did R become known?
Yeah.
Right there. So.
It's a little hard to resolve.
Yeah, it doesn't look like it's in focus to me. I can't seem to get it to. Where's the button? Where's the thing? Menu. Menu. Huh. How do I bring up the menu? I can't get any button to do anything. Well, that's a bummer. I would really not like if it wasn't in focus for me. Zoom focus. Is that doing anything?
Yeah.
Oh, that did something? I can't see it doing anything. Well,
Something 30, maybe?
is that better?
Yes. A lot.
Okay. We'll do it that way. All right. So the question was, where did R get defined? R is defined right there. That's the place where it's defined, and then conceptually, it's right there.
Yeah, I was ignoring it because it's silliness. I got it.
Okay, so now this definition is a little bit complicated to calculate. A little bit complicated to calculate, and I'll show you why. So now we're going to calculate using this definition, and we're going to do it by hand. And because it's a little bit complicated to deal with, and because we're doing it by hand, I'm going to use small numbers because otherwise it's just a nightmare to deal with. So for example, and again, we take the usual convention in math that these clauses are numbered sequentially top to bottom starting with 1. So I want you to evaluate, say, E of something smallish. So how about 11? We'll divide 11 by 3. Now, we all know what 11 divided by 3 is. What's the quotient in the remainder? 3 and 2, right? 3 groups of size 3 and 2 left over. But now the point is that we're going to evaluate. We're going to evaluate this function as it's written. Okay. So we're evaluating E at 11 and 3. Well, which clause are we in? We're in the second clause. That's the clause where there's a bunch of M&Ms in the bucket, right? No telling what the quotient of the remainder will be. So what we're going to do is that we're going to recurse to what value? To what arguments? Right. So we're going to recurse to 8 and 3, but there's a problem, and the problem is that, now this is a little bit sloppy notation, but the problem is that we can't exactly recurse because first we have to remember something. So right here we're going to calculate. Okay, well actually Q0 and R. Q0 and R. Got to remember what that is equal to, well, we're going to recurse to 8 and 3. 8 and 3 because we took away a group. and we're going to have to come back, and I'm leaving myself a box so I can remember, there's still stuff to do. This one, in turn, will recurse to what? Will recurse to, well, yes, Q0 and R. That one's going to end up recursing to 5 and 3. And of course, that recursion is coming from the second clause. Okay. So what will this one do then? Still the second clause. So it's going to recurse to, I didn't plan my space very good, did I? This one is going to recurse to what arguments? So Q0 of and R recurse to 2 and 3. But actually, we're able to compute that. Let's think about this for a moment. This one recurses to 2 and 3. So what's pardon me? What's the answer? We can actually answer this one now. 5 and 3, 2. I got to think about this for a second now. This one has 11. It took one group. This is not good. Yeah. So here we can actually, for this one we can actually answer the question, I guess is what I'm saying. So this should actually be Q and R is equal to, we can just answer directly. Wait a second. This is not good. I don't like this notation. So I'm gonna pretend that it never existed. So this whole thing is just making me sad. Let's try a different notation. Because it's not really managing the problem very well. So we want to evaluate E at 11 and 3. Okay, well, to get this done, we're going to, man, how do we get this done in a notation that's not completely cumbersome?
Do we have to count backwards, or do we have to count Q up from the last instant? Right now, if we do 8 and 3, Q equals 0 plus 1. And then recurs. Remember that. Is there any reason the counter has to come from the end of the row?
Really, yes, it does have to go up from the bottom.
Okay.
Well, I'll just write myself a note here. So, note to self. Note to instructor. Find a better way. Find a mathy way to do this. So there's plenty of ways to do this where you write it that are easy if you do a strategy like this, say, or if you do a strategy like with a table. But I want to have something that looks nice, like with function calls and things like that, and it's just not going to happen on the fly, I think. All right. So now what we want to do is we want to come up with another way to compute Euclidean division. And notice that the points in time where the remainder and the quotient became known are at two different positions, right? That is to say that the remainder became known here by the rightmost 9-year-old, and the quotient became known there by the leftmost 9-year-old. What we want to do is we want to make it to where the quotient and the remainder become known simultaneously. Okay, so does everybody understand, like, conceptually the idea? A sequence of 9-year-olds. We want the rightmost 9-year-old to say, I've determined the correct quotient and the correct remainder here and now. Okay. So we want the rightmost position to compute Q and R. That is to say, if you like, Q will be constant as you move back to the left. Okay, now to get this job done, two days ago in lab, y'all worked on the pyramid functions, right? So the lab concerning the pyramid functions, the request was for you to compute the pyramid function in 3 different ways. One of them was able to be done with a single recursive function, right? One of them was a polynomial, where you had to evaluate a polynomial of n. And then the last one had a pair of functions, right? That was the one that was called TR, pyramid TR and pyramid TR0. So you've got this pair of functions. We're going to need to do the same thing here in order to achieve the effect of the rightmost child, the rightmost 9-year-old, knowing the answer. Okay, so we'll define the following. We'll define 2 functions, t, which has the same signature as e. So it takes a natural dividend and positive natural divisor and produces a natural quotient and a natural remainder. So that's what t does. Now we're defining a pair of functions, so I'll define the other one, t0, as follows. So it will be n cross n plus positive naturals, and then it's going to need actually one more argument, and it will be natural, and it will produce natural cross natural. So this new argument, this third argument that t0 has, the function of this argument, if you like, the purpose, what it actually does, is it's the one that's keeping track of how many quotients there are so far. That's its purpose. And we'll define these in the following way. So as. So the Euclidean division of a divided by b is, so now all that t does, t's like a real manager, okay? It does nothing. It just says, t0, you're going to do all the work. I'm not even going to do anything. t0 of a and b. And when the manager starts the problem, right, the manager, a huge bucket of M&Ms is put on their desk. How many groups has the manager made? 0, right? Hands it off to the subordinate, T0, and says, get started, buddy. So T0 hands it off. There's no groups made yet. Okay. So T0, in turn, needs to be defined as follows. T0 of A, B, and Q0. So Q0, that's the quotient at the present time. Okay, that's how many groups have been made so far. So this is the number of groups so far. Now again, we'll have multiple clauses. So under what circumstance, how do you detect that there's no more work to do? When A is less than B. That is to say, you look in the bucket, you're trying to make groups of size 4, and there's only 3 left. You can't make any more. So in such a case, what is the quotient and the remainder? Not quite. It's 0 in B in the other definition. It's going to be something in B. No, something in A, I mean. But what's the remainder really is A. But, pardon me, what's the quotient? It's Q0, right? So the condition for this, the guard for this clause is that A is less than B. Okay. So otherwise, that means that we need to recurse. We need to recurse, so we'll recurse to self, right? Recurse to ourselves, and say that, well, Q and R should be T0, but now what are the arguments? Well, which variable represents the number of M&Ms? A. A represents the number of M&Ms. So we're asking ourselves, is it possible to make a group? And the answer was yes. So we're going to make a group. So now how many M&Ms are there?
A minus B.
A minus B. And what's the size of the group we're trying to make? B. And what's the quotient size so far? Q1 plus 1 more, or sorry, Q0 plus 1, right? We were able to make one more group. Okay, now, this function seems more complicated than the other one. And to some extent it is. But it has a very nice feature. And that is, as much trouble as I was having on the previous page to evaluate that function, this one is actually really easy. We can evaluate it even for big numbers, and it won't be a big problem. Okay, so for example, please evaluate T, and let's do that same one that we've been saying this whole time. 23 M&Ms divided into groups of size 4. So what does T do? It calls T0. And then what are the arguments to T0? 23, 4, and 0. And why 0? That's how many groups have been made, right? None yet. Okay, so looking at T0, which clause are we in? We're in the second clause. That's the clause where if detected, we can do something. Okay. So that means that we're going to recurse to ourselves, T0. What are the new arguments? 19, 4, and 1. Which is to say that at the present time, there's 19 M&Ms left. We're still trying to make groups of size 4, and at the present time, we've made one group. So, is it possible to make another group? Yes. So we evaluate the second clause, recurse to T0, and so what are the arguments? 15, 4, and 2. So now, concerning the arguments, maybe I'll do one more so that it's as clear as possible. So which clause do we need to evaluate? The second clause. And what are the arguments? 11, 4, and 3. So now, look at the way the arguments are vertically aligned. And look at the vertical alignment of them. The first argument, A. What is A doing?
Decreasing.
Yeah, it's counting down by 4s. That's what it's doing. What is B, the middle argument, doing? It's staying the same. And what is Q0, the rightmost argument, doing? It's counting up. So why is A counting down by 4s? What is that? What is that in the metaphor of M&Ms? Yeah, that's the number of M&Ms in the bucket. Why is B, the middle argument, staying the same? That's the group size, right? That doesn't change during the process. It doesn't change. And Q0, it's counting up. What does that represent? Yeah, the number of groups we've been able to produce so far. Okay, fine. So then the second clause has to recurse to, what was it, 7? 7, 4, and 4. We need to recurse to we need to evaluate the second clause, which recurses to 3, 4, and 5. And then, with arguments 3, 4, and 5, what clause? The first clause, right? And what's the answer? 5 and 3. Which is to say that the quotient is 5 and the remainder is 3. Ah, that's pretty nice. So now I have a different question for you, something to think about because we're more or less out of time. But I want you to think about the following. Suppose that I gave you this request. I said, I want you to evaluate t, function t, at say, I want you to divide 2370 by 11 or something like that. That'd take a lot of steps, wouldn't it? Especially if it was like 23 million and 70 and divide it by 11. That would take a lot of steps. Whereas using the Gradeschool algorithm, that is to say, the little thingy that's inside the house and then outside the house, using the Gradeschool algorithm, you could do that pretty quick, actually. And it wouldn't take you millions of steps, right? So the question is, one of the next things we're going to address is how can we make a function to compute quotient and remainder, but do it in a way that is not horribly slow. Not something that's like, okay, let's take one group at a time. 1, 2, right? In a sense, we want the quotient to count up not by ones, but by the biggest possible number at all times. Okay, so we'll address that next time. Have a nice Thursday. Stay dry.